So this lecture is going to discuss the solubility of ionic solids. And let's return to the previous example we just looked at, where we talked about what happened when we mixed barium chloride with aqueous sodium sulfate. And we saw we formed a precipitate. We actually went through, we wrote out the molecular equation, the complete ionic, and the net ionic equation. What this lecture is going to focus on instead is how can we predict what is going to be insoluble? How could we predict what this precipitate would be without actually performing a chemical reaction, right? So how do we understand the structure and the nature of our chemicals to figure out what's going to be soluble and what's going to be insoluble in water? And first I want to back up for a second and just review charge of ions. So remember, when we talk about ionic solids, it's made from a metal and a non-metal. So a good thing to remember is the alkali metals, everything in group 1 will always have a positive 1 charge. The alkaline earth in group 2 will always have a positive 2 charge. If we flip to the other side, halogens are always going to be negative 1 charge. You should definitely know the charges of group 1, group 2, and your halogens. All right. The transition metal is going to adopt multiple charges, so that's a little trickier. We can look them up. It is good to know that silver will always have a positive 1 charge, though, and aluminum is typically positive 3. Okay, now it's also going to be important to understand that there are ions that are covalently bonded together, and these are known as polyatomic ions. So here's a table of common polyatomic ions. We will use these a lot in this course and if you go on in chemistry. So this is a handy table to just flat out know, both in terms of the names, the formulas, and the charges. So ammonium is NH4+, hydroxide, OH-, sulfate, SO4 2-. And when you think about these, this whole unit carries the charge. And so a lot of times ionic compounds are made of these polyatomic ions. Okay, so let's get back to our solubility generalizations. Our goal is to be able to predict what will be soluble and what will be insoluble for an ionic solid. And so there's a couple ways we can do this. Rather than just present the rules, what I think is helpful is start to see where some of the rules come from. So we can kind of go through this as a thought experiment. And what I have shown here is the solubility grid. And the way you read this is imagine that we have aqueous solutions shown in this column and aqueous solutions shown in this row. And what's going to happen is, let's imagine we mix, for example, 1 and A. So we're going to mix them to have a solution here, and then we'll mix sodium chloride with potassium bromide, and then sodium chloride with potassium carbonate, and sodium chloride with K2C2O4, and so on. And then we're going to fill up this grid. Just imagine taking a couple drops of each solution and ask ourselves, do we see a precipitate? Now, before we do that, what we could start to do is say, let's just think about what ions would be in solution in each of these cells. So for example, if we mixed sodium chloride with our potassium nitrate, the ions in solution, we know we'd have a cation of sodium, an anion of chloride, a cation of potassium, and an anion of nitrate. And all I did was I took our sodium chloride, broke it into ions, and potassium nitrate and broke it into ions. So you should be able to do this with all of the cells. So I'd encourage you to pause the video and do that same analysis so you write down the ions in every single cell you see on this page. Okay, great. Now that you've done that, this is what we should come up with. And again, what did I do? All I did was break each of these apart into their ions and showing 4 ions in each cell and what's present. On the next slide, what we're going to do is we're going to say, all right, where do we see a precipitate? So if we perform this experiment, here's the ions in each cell. Where do we see a precipitate? And it turns out, boom, these are the cells that we'd see the precipitate. Now you have no way of knowing this at this point, except I'm telling you this is the experiment we did, and this is where we see a solid form. So what's not highlighted, all of these cells, no reaction happens. Everything stays fully dissolved. But in these cells, we see a precipitate. So the question is, what is the precipitate in each of these? What is that thing that is insoluble? And we can start to go through it and say in our first cell, B3, all right, so if we look at this cell, we say, what is this precipitate? Well, our choices again are potassium carbonate and calcium chloride. We know those are fully aqueous. Those were dissolved because that's what we started with. And so really we're looking at the crisscross combinations. We're looking at either potassium chloride or calcium carbonate. And so when we think about that, we can rule out potassium chloride because, for example, potassium chloride shows up here and there is no precipitate. So it can't be that one. So the precipitate actually, we can see, has to be calcium carbonate. If we keep doing this, we see in the next one, it can't be potassium chloride again, so it's cobalt carbonate. And then it's barium carbonate. So switch over to the last column, we can do the same thing. We again have potassium chloride, so it's got to be calcium phosphate. It's got to be cobalt phosphate. And it's got to be barium phosphate. Right? And we can start to do this for all of them and say, what is the precipitate? And when we write them all out, here they are. So what was the point of this? The point of this is to attempt to derive a general rule for solubility. And here's our first general rule. If a precipitate will form when the anion and cation are both multiply charged. What do I mean by that? Calcium's +2, carbonates -2. Calcium's +2, oxalates -2. Calcium's +2, phosphates -3. So anytime both your cation and the anion have a charge greater than 1, positive and negative, we would predict that to be insoluble. It will form a precipitate. Now, we can now use this general rule to predict something. So imagine we add another column. And in this case, we're going to predict the solubility of this last row, and we're going to add potassium sulfate, right? And again, sodium chloride, calcium chloride, and going down the row. And we would predict what should be soluble. Based on the rules, what we predict is we should see a precipitate form in these three, right? Because in this case, we'll have SO4 2-, calcium 2+, cobalt 2+, barium 2+. We go ahead and do the experiment and we find 2 of the 3 give a precipitate, but this one remains soluble. And so just to illustrate that we can come up with a general rule of solubility, but they are a general rule. It will not work 100% of the time, but will get us most of the way there. So now that we've seen where these rules come from, let's go through the rules in a little bit more detail. Our solubility generalizations are as follows. Anytime we have combinations where both the cation and the anion are singly charged, these are soluble. So if we have +1, -1, we're going to predict them to be soluble. The major exception to this are silver halides. Silver chloride, silver bromide, silver iodide. These are insoluble. Otherwise, we're going to predict soluble. Combinations where both ions are multiply charged, these are insoluble, right? This is what we just saw. These are going to be insoluble. +2, -2, +3, -3, things like that are insoluble. The hard case of this is sulfates. If you have SO4 2-, that is harder to predict. And then our last general rule is this mixing. If you have +1, -2, -2, +1. If you have only one ion that's singly charged, the solubility can vary. But in general, we can think about if you have alkali metals, it's soluble. Nitrates, soluble. Halides, soluble. So most of the time, these are soluble, but that's harder to predict, right? So these overall are our 3 solubility rules, right? And this is what we should be able to use to predict what will be soluble and what will be insoluble of ionic precipitation reactions. Thank you.